Okay, welcome everyone. It's our pleasure to welcome to Google Neil Gershenfeld. Neil's a physicist, and you often hear about the idea of physics envy from the softer sciences, the biology, and even sometimes the computer science and economics and so on. And I think it's people like Neil that phrase comes from. And not so much the way you usually hear about it of, oh, gee, they've got these nice equations that sort of define the whole world, because that's not where Neil is. Rather, he's embracing this messy world and not trying to solve it with one simple equation, but trying to embrace that messiness. And even more so because he's got all the cool toys. And he gets to play with quantum computing and nanofabrication and nanotechnology and all that fun stuff. So Neil, tell us about your toys.
Okay, thanks, Peter. So there's two ways to view this talk. One is there's three themes that keep coming up in discussions with people from Google on Internet Zero, conformal computing, and field fab for internet access. And so I thought passing through this is a good afternoon to bring them together and take stock of those three topics. And the way I want to do that is I'm here also for an event Ray Kurzweil's doing tomorrow in San Jose. And David Dalrymple is an amazing 8-year-old who Ray and I have been mentoring since he was 8. He's now 14 and a grad student with me. And David wrote this very interesting question where, as far as he can tell, I believe computers as we know them will collapse and become part of reality. And as far as he can tell, Ray believes reality as we know it will collapse and become part of computers. And his question is how to relate those two. And I think that's an accurate portrayal. So what I want to do in the next 45 minutes is talk about how I think computers as we know will collapse and become part of reality. And along the way, hit the areas that have come up in discussions with Google. So I'm going to do this in steps in. The first step, which is a very short-term step, is this is a paper I wrote a few years ago with, I don't know if you know Danny Cohen. He's a very interesting person. Danny's now a distinguished engineer at Sun. But roughly, he was the person who separated what we now know as TCP and UDP from IP. TCP and IP were the same thing, essentially. And he wanted to do early VoIP and said routing a packet should be different than controlling the flow of it. And so he's had this very interesting, he also started Moses. He has this very interesting history of kind of teasing out nuggets. And Danny had looked at what to me was just an engineering hack. We, a number of years ago, were looking at kind of device physics of people and computers interacting and had done a bunch of test beds. This was for the White House, for the Millennium, a series of installations like a bathroom shelf to manage medication. This was furniture in the Museum of Modern Art to navigate information without what looked like computers. A stage for the Flying Karamazov brothers to juggle sounds. This was a building as theater in Barcelona where the building itself was the performance each night. And in each of these, we were doing something else, but had to connect stuff to a network. And it cost too much in dollars, pins, power, watt, a lot of resources. And we ended up doing a very simple trick, which was bits have a duration and a speed, and that corresponds to a size. If the bit is smaller than the network, it sees it. If it's bigger than the network, it doesn't. If it's bigger than the network, you can then ignore the network. And so it's sort of like Morse code. We would just hit whatever the medium was, make a transient. This is a few hundred nanoseconds of ringing, and then just simply time the transients. And so just like Morse code. And what was nice about that is you could do it over any topology, and you could do it over any link. You would just kind of hit it and time these transients. And the only good parameter you believe is the onset of this transient. So for $1, you can make a web browser, but more than that, a web server. But more than that, it can communicate over any physics you give it of wired or wireless. So that wasn't research. That was just an engineering hack in support of those projects. And the name Internet Zero emerged from an Internet 2 architect kept saying, how fast can this go? And we were explaining that it's bad to send broadband video to light bulbs. So it's not Internet 2. And I just said it's Internet 0 to try to shut them up. But the name stuck. And it's pretty accurate as a layer below what you can think of as Internet 1. And so this is what an I0 packet looks like. It's self-clocked, so there's no performance numbers. This is something Danny had stressed. One of the reasons IP scaled is unlike almost any standard you know, it's not tied to performance numbers. And so in the same way, it's self-consistently self-clocked and is just transients. So this is an I0 packet, and it looks like a barcode, and that's the point. You could read it optically and put it in a wire, and it would be a valid packet, and you could blink lights, and you can play it acoustically. And so Danny then pulled together Bob Kahn and Len Kleinrock and a bunch of his internet architecture buddies. And what came out of that meeting was this very interesting parallel. I still considered this a $1 engineering hack, not a subject of serious study. But there was this very interesting parallel that back when the internet emerged, what's now motherhood and apple pie is there were packet switched networks, and they were dissimilar. So SatNet and PRNet and ARPANET. And either they didn't talk at all, or you had to configure state at the boundary. And in fact, in this slide, I had red blocks there, and Bob Kahn asked me to take one out, because one of the bigger problems wasn't just you had to configure state. There was no state that you couldn't get from one to the other. And so the solution back then was to agree on a representation of a packet that's independent of the medium that transports it. And so we now have IP. But today, think about the stuff around us. If you want to do, say, 802.15.4 to a wireless device, and ERDA to an IR device, and home plug to an AC power line device, and ISO 18000 EPC to an RFID tag, they have nothing to do with each other. And so if you want to go from like RFID to IR, they have nothing to do with each other. You have to configure state at the boundary, or they don't talk at all. And it's really exactly the situation the internet was in a few decades ago. And so in retrospect, this didn't start as a project to solve this problem, but in retrospect, what was going on is by agreeing on a representation of a packet that's independent of the medium, it's recursing on the original architecture of the internet down to the physics. And so it means you do inter-device internetworking. Instead of internetworking at layer 3, you effectively internetwork at layer 1. So to go, oh, I don't have the rest of the picture here, but to go from ultrasound to optical to IR, it's all just timing transients. And you just simply change the transients from one medium to another. And that's familiar from Morse code. When you flash it on a light or click a telegraph, you don't change Morse code. But today, just about all the standards we use, like 802.15.4, specify the medium and the data rate and the framing and the encoding and absolutely everything. So Internet 0 emerged as really a layer below the internet. It's suboptimal, and that's the point. If you want to saturate channel capacity, don't do this. But if the biggest problem isn't throughput, but the cost of complexity, then it makes sense to internetwork, just like IP is suboptimal for everything, but just good enough for almost anything. So that's where Internet 0 emerged from. And I have a bunch of these with me. This is a $1 device, and it's IPv6 stack. It runs a web server. It switches a couple amp load, reads sensor inputs, does peer-to-peer associations for control systems. If we have time at the end, I'll set it up and do a demo of web pages from it and building distributed control structures. The reason it exists, then, is again, this was just this engineering hack for projects. The internet architects got interested. Then a couple things happened. Greg Papadopoulos, Sun's CTO, volunteered a standards person to help develop a standards process around this. And then there was a very strong reaction from the building industry. And so that's what's really driving it. And in turn, energy is really what's driving it. So there have been countless attempts at smart homes, smart buildings that on balance haven't been all that exciting or that significant commercially. On the other hand, in the US, building buildings is $1 trillion a year. It's so big you don't notice it. The cost of labor in the building industry is $300 billion a year. It equals the whole IT industry, just labor for building buildings. So there's this huge overhang of an industry much bigger than just about any industry you can think of. And Cisco doesn't make anything relevant to them, essentially, to first order. Because when the cost of labor is $300 billion, you're doomed if the light bulb needs first a network installer to install the light bulb and then an IT department to run the light bulb. So the interesting in Internet 0 wasn't the throughput to the light bulb. It was getting rid of network topology by just using these transients so that the skills, you have to service the light bulb with energy and information, but there is no architecture beyond that, turning it back into what electricians do. The initial interest from the building industry was the cost of configuration, that in this room, somebody has to make a wiring diagram of what switches go to what lights and what thermostats go to what VAV units. So the initial interest was just soft state, that occupants can make the associations as a distributed data structure. But then as energy exploded, what really has taken off is this energy is the killer app. Buildings in the US use 40% of the energy. They use 70% of the electricity, not industrial processes, just buildings being buildings. So 70% of the electricity. And of that, a number of different studies come to the same conclusion that about a third of it is wasted. Now, the third that's wasted, some of that is for inefficiency, like those light bulbs over there don't know the window's open and it's a sunny day. And in between deciding are the lights on and off, the light bulbs can't adjust to what's the natural light and the air handlers to what the window is doing. The bigger one, though, and this was really eye-opening, is it's hard to quantify, and we're trying to quantify, but it looks like a larger fraction of that isn't inefficiency, it's over deficiency. It's warring subsystems in buildings. It's like heaters and coolers running at the same times, and fans blowing against each other, and just valves that aren't opening, and just this sort of sea of broken stuff and misconfigured stuff. And it's familiar if you think about running a network, all the things that go wrong and you would fix. But buildings don't have the intelligence to find that. So there's all of this over deficiency in how buildings are running. So numerically, it's the biggest energy win available. It's a number of tens of % of 3/4 of the energy. So why hasn't it happened? There are a whole bunch of reasons, but the starting point is to add a control point to a building today is maybe $50. Because first for the device, and then for the installer, and then it goes into a central control system, and somebody has to modify the central control system for the control point you added. And so this is exactly the BitNet era, where you had to add a mainframe and configure the mainframe. And what you need is an internet in buildings. You need to incrementally extend the building when you have one new sensor or actuator to bring it down to the incremental cost that's $1. And so the interest in retrospect in Internet 0 is by getting rid of topology, you can make internets in buildings. They're suboptimal for performance. It's a microsecond over a building, so it's about a megabit is the data rate, so kind of DSL speeds on down. But in return, you can get rid of topology. So what that's growing into now is a project I2E, Intelligent Infrastructure for Energy Efficiency. This started from a core team working on Internet 0 of companies like Cisco and Schneider Electric. If you don't know them, they're Square D, Industrial Controls, to Andover Building Controls, Juno Lighting, much of the electrical industry, commercializing this. But then we started working with the national labs, Argonne National Lab, National Renewable Lab, that had building efficiency programs, but not really a technology platform to implement essentially a building internet. That wasn't their skills. And so this has grown into a larger program with Department of Energy, and then a number of utilities and energy labs in other countries, starting with this bottom layer of IP over anything to anything at the cost and complexity of what electricians do. Adding the fine-grained sensing and actuation, online measurement, modeling, and prediction, distributed control systems, then interfaces with people, and active and passive building systems and utilities to really scale up to do these tens of % recovery. So that's turning into the forcing function to bring IP to leaf nodes. And I think, in turn, that's going to drag many other things behind it. But energy is what's really going to bring this into the infrastructure. So we're just at the point now of this was a test bed of hundreds of nodes, and we have some early field trials in buildings, seeing really appalling things. I was looking at the data from one building just at MIT, where instrumenting it with this, the cooling time constant was 20 minutes, and the air conditioner turns on at 4 in the morning to get the building ready for everybody. And everywhere you look, there are these horrible inefficiencies just because you can't see what's going on. Oh, and yeah, this was a fun recent test bed. In the Venice Biennale, a group of architects we work with, coming out of that Barcelona test bed, did essentially hyperlinks for reality. They made cartoon versions of all kinds of furniture, and then this is all a big Internet 0 network. And then it's interfaced into a virtual shared environment with these hundreds of objects. So like when you make paella, your paella pan tells your friends you're making paella, and when you go to the fridge, it talks to your, the different spaces you're in have shared spaces, but in the object. So it's playing with kind of hyperlinks for reality, building on these devices. So that's bullet one. And this isn't very far out. This is it's getting commercialized now by the kinds of companies I mentioned, IP over anything to anything for $1. Not competing with all the stuff you know, but really a layer below it. Now I'm going to go one step further out. Bill Butera was a grad student who came to me with a vision, and then he carried on with this to Intel. He didn't want a web server for $1 you can put in a switch or a light bulb. He wanted to just paint the computer on the wall. And if you didn't have enough computer, you'd put on another code of computer. And so he was a former chip designer. And so he was asking, how would you program a paintable computer? And so this was push pins with ARM processors emulating a few millimeters of silicon. And it's a PostScript interpreter. This is PostScript conventionally interpreted. Here, these are doing short-range, probabilistic, local memory sharing with mobile code. And then they're just statistically, by looking at the propagation of messages in the network, inferring geometry. And then they're doing a pigeon subset of PostScript, but real PostScript and stroking letters. So to make a PostScript interpreter, but unlike this projector, if you need more PostScript, you make it twice as big. And if you shoot a gun through the middle, nothing happens. And the medium is the PostScript. There isn't an I/O processor and a RIP processor. And so that was an existence proof you could do something like this. It had a lot of constraints, though. These were fairly heavyweight. There's lots of code. And one of the biggest constraints was we had a compiler to go from problems like this, distributed data storage or sensors or graphics, to mobile code. And the compiler was Bill. You would say, Bill, I want to do a distributed data storage. And he would think about it and write some probabilistic shared memory mobile code, and it would work, but couldn't really tell you exactly sort of quite why or how. And it was hard to automate Bill. And also, to really physically maintain, needed breakthroughs in many different areas, in powers, packaging. And so paintable computing is expanded into a broader program to do conformal computing. So in conformal computing, what we're trying to do is make computers that, unlike a box, can cover surfaces and fill volumes. They can be incrementally extended. So if you need 2% more server for 2% more hits, you just open the top and add 2% resource. You can change form factors. It's physically distributed for distributed problems and operates reliably with unreliable parts. So I'm going to come back to the physical embodiments, but we're doing this from high-performance computing limits to arrays of commodity microcontrollers to ASICs we're developing that do this, down to scaling to nanostructures. But the question is, if you have resources like this, how do you program it? Now, the endpoint we can see, these are a number of different projects Peter alluded to at the beginning. This was one of the world's first quantum computers. This is a crypto system in optical propagation. In each of these, each logical degree of freedom in the computer is a physical degree of freedom. These are computing in exactly you understand computing. There's bits and they do logic. But there's one physical degree of freedom, a photon, nuclear spin. And each physical degree of freedom is a logical degree of freedom. These aren't yet very large computers, but they're computers at that limit where the physical degrees of freedom are the same as the computational ones. At that point, you really can't maintain the fiction that computer science is distinct from physical science. So the reason Center for Bits and Atoms exists is I never understood that boundary, and a number of colleagues. If you think about the projection on physics and chemistry and math, there's information, the bits, and there's the physical property of the atoms. And I never understood the boundary between it. And from the 50s forward, computer science has essentially sought and succeeded to hide the physics from the programs and the programmer. So you operate in an abstraction, and then there's many levels of description before you get to the physics. But that abstraction is beginning to break in lots of different areas. It's breaking in, if you look in high-performance computing, in interconnect bottlenecks, in total power budget and power density, and just cost of taping out and shipping software. Maintaining this fiction that the software lives in this airy, abstract universe, unanchored by the physics, requires more and more heroic engineering to maintain the physics. Instead, when you get to this point, you just can't do it. It's the same variables. And so I want to argue that the only scalable model of computation is physics. The model of computation has to have the same variables and same resources as physics and scale the same way as physics does. Otherwise, it's a fiction that you're trying to hide. And so I want to show you emerging insights into what does a low-level language, a high-level language, and an operating system look like that has the same resources as physics and scales with the physics. So an inspiration for this was a beautiful thesis in the 70s Roger Banks did with a thesis of Marvin Minsky and Ed Fredkin. And it was just a theoretical question, are cellular automata computationally universal? So it's a very simple CA. There's a 1-bit state, and there's only 3 rules. And with those 3 rules, that's a wire, that's a corner, and that's a Boolean gate. And so he showed you could do Boolean logic. It's excruciating to do it this way. You wouldn't want to do it, but it was a constructive proof of the universality of CAs. But we were inspired by that and have cleaned it up to map it onto both the needs of computing and the needs of physics. And so the modern version we're doing of that is asynchronous logic automata. So there are cells. Each cell implements a logical operation. So we're not using lots of cells to construct a logical operation. That's the primitive. And then there are tokens that can be 0, 1, or empty. And each logic cell waits for valid input tokens and an empty output token and pushes the state. So here are logic gates. Those are interconnect cells. It's a crossover. These are ones to create and destroy these asynchronous tokens. And then there's a stem cell I'll talk about at the end. So you should think of this as cartoon physics in that in this world, essentially space equals time equals state equals logic. What I mean by that is there are no wires. There's only interactions of cells. The distance you travel equals the time it takes to travel. It equals the number of states you can store, and it equals the number of logical operations you can do. Usually those are completely different resources, but because each is represented locally, they all scale the same way. It means we propagate by propagation delay, but that's a few orders of magnitude slower than light. State-of-the-art propagation is picoseconds over microns for a fast transistor. And so it still is nanoseconds per millimeter, which is on the order of speeds you run chips at today, limited by other things, so it's not a severe cost. So in this asynchronous logic automata world, for example, here's a linear time sort. It's for people who care about sorting, it's the structure of an odd-even sort, but it's kind of unrolled as a picture. These are comparators here, and then these are switchers. And so the data goes through the comparators, and then it gets either switched up and down and runs back and forth. And it takes linear time for data to go from one end of this to the other. So it's a linear time sort. And there's nothing special going on. It's just when you do n log n sorting, you're not counting the order n storage of the data that you're sorting. But here, storage costs the same as computation. So the storage takes an n-squared algorithm and makes it order n. Here's a router. This came up in incremental extensibility of routing. So here are routes. Here's how you check the route. But this is a router that's just sort of an extensible medium. And so I'll show implementations. If you need more router, you just make the picture bigger. The router isn't defined by the granularity of, say, a content addressable memory. This is a cryptosystem. It's a Feistel cipher reduced down to the logical essence. So here's the letters CBA going in. And then in a second, you'll see coming across, this is the S box. These are the bit rotations, and here's the XOR. So that was an encryption round. This is like the structure of DES, a Feistel cipher. Here's the decryption round. So this is a stream cipher. But again, if you want more stream cipher, you just make the picture bigger. Multiplying bit strings is linear. So you don't need floating point because you can do large fixed point, because multiplication is linear time, because it takes linear for the information to get one end to another. And in turn, multiplying matrices is linear time. If you think about the distance it takes a vector to go through a matrix, the distance is linear in the matrix, and that's the execution time. So you don't need fast Fourier transforms. You can just do any matrix math in linear time in this world. So what's the cost? This is an ALA, asynchronous logic automata cell. In CMOS, it's order 1,000 transistors. This is a non-reconfigurable version. I'll show you reconfiguration. It's order 1,000 transistors. That means if you virtualize with 1,000 virtual cells per one of these, it's roughly a 1 transistor overhead. So at somewhere between 2 to 1 or 1,000 to 1 the density of DRAM, based on how much you want to virtualize, you turn storage into computation and interconnect. So the overhead really isn't that large to do this. But even more than the overhead, what I find so encouraging about this as a direction, where you should, again, think of this ALA world as kind of a cartoon physics world that we compute in, is one version we're doing is low-level code for multi-core processors for looking at limits of high-performance computing. Programming the biggest machines is a serious obstacle for like getting towards exascale computing. And so the ALA abstracts out which particular processes are in here and how they're connected, and all they're doing is event updates in the asynchronous rule table. These are arrays of commodity microcontrollers. You can get 20 MIPS for 20 cents and 2 millimeters in a little AVR core today. And so this is sheets of commodity microcontrollers, and this has arrays of LEDs on the backside to make a display. But it's a display where you can cut off as much as you want and do I/O anywhere. And crypto or graphics is implemented extensively in the display, not in something controlling the display. These are ASICs based on what I showed you. This is prototyping nanostructure logic. But the key thing is, unlike, say, Intel hex code for an x86 versus an ARM, this ALA representation scales across all of these. It's kind of cartoon physics that as long as you're making a computer that runs in our universe, it sort of has the same rules. So it's a representation that runs unchanged on each of these. It's kind of a lower level microcode that has this portability. A second implication is the local yield only needs to be 1,000, not 1,000,000 or 1,000,000,000 transistors. So you can be much more aggressive in the fab process because you're not yielding a big chip. You're yielding lots of tiny parts. Another is power, because power is only consumed where things are happening. The hard thing in asynchronous computing has been, how do you make a design asynchronous? In what I showed you, I didn't design for asynchrony. I just designed logical relationships. But because every single bit is a processor, each bit processor can enforce the asynchrony. And it only does something when there's something to do. Speed, you don't have to clock it runs a gate propagation delay. The scalability comes from, we've abstracted these objects to just this medium, so you add more medium. And the hope, and this is still very much a hope, not a proof, is because we've gotten rid of a lot of the architecture, it simplifies a lot of the programmability. So I want to talk to that point now. Once you have this computing medium, how do we program it? What I showed you, the examples, were done in something that looks like Verilog. When you design a chip, you use typically VHDL or Verilog. Instead of drawing it, it's a programming language for the circuits where you express the relationships. And so this is a Verilog-like language. But the only difference is when you do Verilog, it's followed by a netlist and place and route. Here, each of these statements, these words, is an object. And so to say them is effectively to place them. And so the Verilog directly maps onto the structure it's describing. And so the examples I showed you were all done that way as a bottom-up. A mid-level one we're doing is visual data flow. But the visual data flow is directly executable. It's turtles all the way down. The picture of the visual data flow itself is executable. You don't need a scheduler to execute the visual data flow. But the most interesting one, and this is the most speculative one, is in physics, there's an equivalence. When I throw this up, you can do this as Newtonian mechanics. Or you can just say, this object is minimizing the action. So it's going to choose the path of minimum action. Or you can view the light here as minimizing the transit time. Physics has these equivalences of local and global descriptions. And they're completely equivalent. And they come from symmetries and conservation laws. Once you have symmetries and conservation laws, you get these equivalences. There's nothing like that really in computing, because this computing object breaks every imaginable symmetry. On the other hand, this ALA is a uniform medium. And so we're interested in revisiting. It's essentially constraint programming, but now constraint programming where there's a direct mapping onto its solution. So I showed you the sort example before. Let me show you sort done this way. here's a funny way to sort. You can take an unsorted list. You want to find a permutation matrix, weight it by indices into the matrix. And it's maximally sorted when you multiply big numbers times big indices and small numbers times small indices. So this is a statistic made extremal when you've sorted, and with constraints that rows and columns are normalized to 1. You can then do relaxation to turn these into real valued variables in the permutation matrix that let you go in the interior. For the experts, you then look for a dual which captures the locality to do the optimization. And when you do the dual, what you get is what essentially looks like an auction. You have nodes, and they bid on variables, and then the variables kind of go based on the local auctions on the nodes. But those words aren't where this came from. This is just a dual decomposition mathematical program. I'm adding the words to describe it. But what's interesting is if you look at essentially what this auction is doing, it's the sort I showed you with one extra step. When you write variables that are a vector, they have coordinates in whatever space you're in, preferences, feature vectors, but they also have coordinates on the piece of paper you're writing them. And essentially what we're doing in this conformal computer is we're implementing the piece of paper. So when the vector gets multiplied by the matrix, we're actually implementing the space of the mathematical symbols as the computation. And so with that identification of the representation onto the spatial structure, then these equations essentially become the sort I showed you. That's not automated, but it's a sketch of a workflow to go from a global statement to this distributed solver. And in fact, those ideas are proving to be very powerful in reverse engineering the internet to show what it makes extremal, and then use these distributed optimizations to forward engineer protocols as dynamic solutions, not static protocols. So asynchronous logic automata is a programming model that locally looks like physics. Now, constrained optimization is a way to make global statements into distributed solutions as a sketch of what a compiler might look like from a high-level statement. Next is, what does the operating system look like? Today in the OS is like a hand of God that can reach into the computer and do stuff. But if the computer is this extensive medium, you don't get to reach in as a hand of God. The operating system has to be in band. And so here's an example of loading the sort. What I'm doing right now is I'm streaming in a folding path. Then on that folding path, I'm streaming in a configuration. And I'm doing it by sending data. So the data is the same data the processor uses, but now I'm using one more type of cell, a stem cell, a reconfigurable cell. And the reconfigurable cell is turning into processor cells by the data streaming through here. You can just barely see that blinking. Now, the interesting thing here is this is all running asynchronous and unclocked. As these get connected, you'll see a little blinking because they have something useful to do. Then they don't have anything to do. But watch what happens when it gets to the very end. Once it finishes a frontal propagate of consistency, and now everybody has something to do, and the sort turns on. And you didn't have to figure out how to schedule the execution and distribute the clock. Just everybody had something to do, and now the sort's running. And so that's a way to load a program, if the program is, say, this screen, by coding for its construction. Now, that in turn has a very interesting implication. If a program is a shape and you can code for its construction, you can code for other shapes that are shapes. So this is actually part of a CAD workflow to take mathematical descriptions of objects into folding codes. And the reason we're doing that is this. This is a thing I did a year ago with Manu Prakash. This is a computer where what you're looking at is high-speed video, many kilohertz video. These are 100-micron channels. These are bubbles, in this case, nitrogen and water. And this is a 1-bit memory toggling. This is a ring oscillator. This is a bit triggering a bit that triggers a bit. And then this is combinatorial logic. When two come in at the same time, they go out in both directions. When one comes in, it goes out on the left. So that's a logic gate. These are stages in combinatorial logic. So I just showed you all the things you do for any digital logic family. Nonlinearity gain, fan out, persistence of state. But here, each bit is a unit of information, but also a unit of material. Second piece is, this was something Saul Griffith did in his thesis. These are mechanical strings that interact magnetically locally, and they fold. So instead of having today, like metrology in a control system, these strings mechanically fold into shapes. And so these two slides together are the ingredients you need to take everything I showed you, but now not implement it virtually as electrons in a computer, but implement it as physical objects. And the reason we want to do that is we want to create life. There's a hierarchy of simple self-assembly to coding for construction to programmable assembly with algorithms and ultimately biology. And there's a range of length scales, somewhere between, in nanometers you can do this with life. Large length scales you can do it anyway, but there's a mesoscale that's very hard to fabricate complex structures. And so we, CBA and Harvard and Makani Power with DARPA support, are taking everything I showed you, but now implementing it not electronically, but physically. And the purpose here is not math, but construction. We're re-implementing molecular biology instead of at nanometer on micron to millimeter scales, equivalence of enzymes and proteins and folding and replication to code for construction. So here's an example of a workflow. Here's a wrench. And then this is videos from Jonathan Bachrach at Makani. You can decorate the wrench to find a Hamiltonian path, a continuous path through the wrench. You can then take that wrench and put it into one of the strings I showed you, now running in 3D. And so what's happening is each of the cells locally is trying to drive its neighbor into its desired configuration with no global knowledge. And then you get the global wrench by folding it from the local string. And then if you send in a different ALA folding code, the same string.
Is this just a simulation, or can we actually do it?
Well, this is more than a simulation. This is a design workflow from CAD to physical modeling. The project is to do it physically, and we can do it on short strings, and the next few years are to do it on longer strings. There's a lot of steps to go from this at microns, but we can fold short strings this way, and the project is to take the couple slides back and scale that. So what that leads to is Shannon took us from analog to digital communication that lets you error correct and communicate around the world. Von Neumann took us from analog to digital computation. This was the last great analog computer that got worse the longer it ran. Now we have Pentiums. But making chips and airplanes is still a fundamentally analog process. And what's emerging is the real killer app of everything I'm telling you ultimately is to digitize fabrication, just as happened in the 40s and 50s for communication and computation. And so coming to the last thing I want to talk about, to do that research, we spent millions of dollars to buy machines that makes anything. I started a class, How to Make Almost Anything, that was to teach students to do the research I'm showing you. But I was swamped with students not there to do research, just to make stuff. So Kelly was a sculptor with no engineering background, and this was her semester project.
Hi, I'm Kelly, and this is my screen body. Do you ever find yourself in a situation where you really have to scream, but you can't because you're at work, or you're in a classroom, or you're watching your children, or you're in any number of situations where it's just not permitted? Well, Screen Body is a portable space for screaming. When a user screams into Screen Body, their scream is silenced. But it is also recorded for later release, where, when, and how the user chooses.
And going into the main building, up to the second floor.
This is a web browser for parrots. It lets parrots surf the net, talk to their owner. This is an alarm clock you have to wrestle with and prove that you're awake. This is a dress instrumented with sensors and spines that defends your personal space. Each of these was a semester project in the class. And this happened so consistently, I realized the students were answering a question I hadn't asked, which is, if we implement this whole digital fabrication roadmap, what's it good for? And go back, Ken Olsen, the head of digital, famously said, nobody needs a computer in the home. DEC's bankrupt. You have a computer in the home, but it's not for inventory and payroll. In the same sense, you can look at these and say, saving screens or web browsers for parrots or defensive dresses are fun and frivolous. Now we'll talk about things that make money in a real business. But as you know so well, personalization, customization is what really is driven just about any technology. And what the students were doing is personal fabrication. And the point of this is not that it's a scalable business model and not that it's mass produced. It's not stuff you can get at Walmart. It's stuff that you can't get at Walmart. It's stuff for a market of one person. It's exactly personal computing, but now for fabrication. And it's one of the strongest technical forces I've ever seen in technology. Every year on campus, I teach this, and it's just overwhelmed with students desperate to take it, to create this stuff. So that, in turn, led to a little outreach project. NSF said, we spent so much of their money, we should do some outreach, and we thought it would be boring to have just a website or a class. So we set up little prototype tools in the field, and we just did one in Boston, and it had a very unexpected result. Volume up.
Solutions for the world we share. Principal Voices, in association with Shell.
We've had a digital revolution, but we don't need to keep having it. We can declare success. We won. What's coming now is the digital revolution in fabrication. My colleagues and I started teaching a class called How to Make Almost Anything. And the idea was just that. It's a program looking at how the digital world relates to the physical world. And one of the core things coming out of the research is the idea of digital fabrication, making the Star Trek replicator, an assembler that makes anything you want by building the atoms on up. This is designed where you put in the ribbon. Millions of dollars of equipment at MIT are like the mainframes of digital fabrication. We can make anything we want using those tools. In 20 years, we'll make it so you can have it in the home. The fab labs are in between. They spread all around the world, letting ordinary people create technology from South Africa to the north of Norway and from rural India to inner city Boston. Instead of spending vast amounts of money to send computers and energy and communication around the world, you can spend much less to send the means to create it. Energy, communication, computation, just to say the words, they sound big. They're being tackled as billion-dollar mega projects top down. Fab Labs is tackling them from the bottom up. We're just finding so many people with such interesting inventions and such great ideas. Sharing that is where I see this going.
So where that was shot is a few hundred miles above the Arctic Circle. So far north that satellite dishes look at the ground, not the sky, because that's the way to the satellites. And I didn't wake up and figure you need these tools there. We did one in inner city Boston. It's about $50,000 in equipment that sort of approximates both what you can do on campus and what you'll eventually be able to do when we can do the fully coded construction. But from inner city Boston, it went to, this is the coast of Ghana and Sekondi Takoradi, and this is Soshangovi, a township in South Africa. That lab in Norway, rural India. Just about every single day I get messages now, I want a fab lab. And about once a week somebody cancels their life to devote themselves to this. And they want to know where to report. And we didn't make this up. We didn't think this up. What's happening is it's not a digital divide. It's an instrumentation and a fabrication divide. People who want to measure and modify the world, not just get information on a screen. So there's a kind of a flow we've been seeing in the projects. It starts with technical empowerment. These are young girls who made a few $100s on a street corner in Boston doing rapid prototyping with a laser cutter, to informal technical education. We had set up that lab in Ghana, and we had designed a little network sensor. And then there was an 8-year-old girl who wouldn't leave until she had made it.
Yay! Go on inside.
So maybe 1K cellular. Maybe
My name is Valentina Kofi. I am 8 years old. I made a stacking board.
So this girl in this Ghanaian coastal village has fabbed the board. She's doing surface rework. She's about to load the microcode. Can all of you do that? So there's a sense in which she's not just catching up, she's kind of skipping over. Then these labs started doing useful stuff, like instrumentation for agriculture, turbines for energy. This was rapid prototyping of the housing, using the tools to make house-scale parts. And then 2 projects, again, these weren't meant to be useful, but that grew up in the field I wanted to mention. This is one on how do you bring internet access to all the places, like this shantytown in South Africa. So instead of mass producing a computer that you give to the world to solve its problems, what I have here are these parts. This is about $10 in parts that you make in the lab. It's about 10 milliamps. And what it does is it implements Internet 0. It does the network protocol. It talks to a PS2 keyboard. And it does NTSC PAL video. And then what I have here is a $50 Cisco Linksys access point that we're using as a server. So this is a very thin client, so thin that our server is at the cost and complexity of what most people think of as a thin client, and then the thinner client. And so if we set this up, I can show you this is it doing Gmail. This is Google News. And these don't all need to be the same. This is aiming at the space in between SMS and Windows. But for $10 and 10 milliamps, you can produce your own internet access. And they don't have to all be the same. You can have ones of different sizes, different languages, different skills. And the skills and jobs are local, and the supply chain is local. And then, in turn, you need to make the connection. And the issue generally is the existing telcos are terrible. But regionally, there are fiber backbones getting pulled. And so these are processes in the Fab Lab. This is using a vinyl cutter to make a smaller folded dipole array to do roughly 1 to 10 kilometer. And then this is using a bigger tool to make antennas to go up to 100 kilometer scale. So these are the tools to make the high gain links, initially using these Cisco access points, and then looking at the Internet 0 radios. And so these two together are a way to use field fabrication to do computing, not with heroes in a place like this coming up with the computer and then giving it to the world to solve the problems, but providing the tools. Now, this doesn't scale to the regional on-up network. You still need managed infrastructure. But for the last, say, 100 kilometers down to the terminal, you can really do bottom-up, not just use of computing, but design and production of computing. And so this is at the stage of just going into field trials and beginning to look at larger scale fan-out of that. So I want to close with, if an 8-year-old girl in Ghana can make her own internet terminal, it just breaks the boundaries here in the valley between research, education, aid, industry. It's sort of all of them and none of them. So to keep up with that, we're spinning off 3 organizations from this Fab network. One is a fund to do micro VC. Microfinance has fan-out, but it's banking. VC you know well, but speculative technical risk, but that doesn't do fan-out. If you can make an internet terminal for a few dollars, it's a great business model, but you need global capital to go to local inventors, local inventions to go to global markets, and production not in Flextronics, but in local sites all over the world. And so the Fab Fund is putting together the infrastructure for that. There's a degree program for amazing students like that 8-year-old girl who are refugees from broken school systems, where instead of coming to a place like MIT, the lab network itself becomes the campus. And finally, a foundation to support the operational scaling. This is that lab in the north of Norway. It's run by a Sami-descended herder. But if you look at it, I went to MIT for the machines to do research. And there's still plenty you can do at MIT you can't do here. But a lot of what I went to MIT for, you can do there now. I went for the libraries. Those are certainly online, thanks in part to Google. And I went for the people. We run a broadband video MCU. And so I see the people in the Norway much more than my colleagues at MIT. We're all too busy to talk on campus. So the assumptions of a central research lab like MIT are beginning to not make sense. There's still things you need MIT for, but there's a boundary where instead of assuming all those things are scarce resources, they can be globally distributed. That's the ultimate impact of digitizing fabrication, but the kind of pleasant surprise is we can do it today. And just a final note is all the infrastructure to create this network is being used for one other very amusing project. There's a fun group of people. like the animal behaviorist Diana Reese and Peter Gabriel and a few others, who've started looking at stuff like this and thinking about animals. And so the project that's just starting, and this is just a passing note that it's ramping up, is an interspecies internet, doing everything I said, where instead of people, it's animals all around the world interacting with animals and interacting with people. And we're just starting early trials of that. So stepping back, everything I showed you is linked off the site and in these books. And the flow is Internet 0 is a short-term thing, IP to leaf nodes for $1 driven by buildings. Conformal computing is sort of middle of the field of view. How do we scale high-performance computing? And I want to argue very strongly it's by recognizing that computer science really needs to revisit assumptions in the 50s and look more like physics. And when you get that right, the computing scales with the physics. And the last piece is when you connect that to the physics, it means you can make programs, but also things in digitized fabrication. And the close to home message is internet access can come from the bottom up, not mass produced from the top down. So with that, thank you, and I'll be happy to take questions.
Is this empowerment of individual people put you on collision course, at least with certain governments and certain jurisdictions, like regulated spectrum and so on?
So the question is, what about governments and jurisdictions? So the amusing story about that is this picture is taken in South Africa, where we're doing field trials. And in doing those field trials, we broke a variety of laws. And the agencies whose laws were being broken had people within them encouraging us to break the laws. There are plenty of people who didn't like it, but there are plenty of people in the agencies who recognized that it just didn't make sense, and they liked it that we were doing a demonstration project that showed it broke the laws. So there are a lot of regulatory issues, but ultimately it's just too leaky. You can't control this. Or another version is we deployed one of these labs in Afghanistan this summer, and it was in partnership with, among others, military agencies. And we had interesting discussions with like rooms full of generals, where half the room would say, my God, we have to classify this. And the other half of the generals would say what I would say, which is first, you just can't control it. It's not a controllable resource. But more than that, blowing people up is a mature market need that's well met. You don't need all of this to blow people up. There's good ways to do that already. It's to kind of meet all the other needs that are less well met. And that's what was really behind sending the lab to Afghanistan. So it leads to very unusual partnerships. It's not that it's all yes or all no, but they're strong advocates in agencies you might think would be opponents.
You showed a bunch of problems that you can do in linear time in your model. I was wondering, what is an intractable problem in your model? And for example, can you translate the P versus NP question there?
First, the linear time trade-off is very easy to understand. Let's see if we look at, oh, I don't know any of these. The linear, or actually, let me go back to this. The linear time trade-off is simply each bit is a unit of time, space, state, logic. And so it's an order n win. So you get to take order n off almost any algorithm, because each bit of either storage or communication becomes a bit of processing. So it's no more than that, but you get order n off anything you can think of. And so there are a couple places that's really important. One place that's dear to me is I'm hoping we can finally bury floating point numbers, in that fixed point math, it takes 1,000 fixed bits to equal double precision floating point. And since we can do this in linear time, I think we can get rid of floating point numbers. A second huge one is matrix math is linear time, so you don't need fast anything, convolution, just about any matrix transform. But it's for structured things like that. It's not for all algorithms. It doesn't. It's order. It's one n speed up. It doesn't change other classes. And so it's a reason to do this, but all of these are other reasons to do this. Order n is a very nice result, but I don't want to oversell that. It doesn't fundamentally change computational complexity. It just changes the one factor of n in the scaling. But it's a big factor of n.
You mentioned that with the Internet 0 stuff, you have a lot of cheap nodes that are running IPv6. How do you allocate addresses on that? Do they each have their own MAC address as you would on Ethernet? And then are those globally routable?
In this Internet Zero world, there is no MAC. We've essentially collapsed layers 1, 2, and 3. They're all the same thing, meaning that the packet is the logical description, it's the medium access, and it's actually what's in the medium. So there is no MAC. There's just IP addresses. Routing it is up to how you want to handle the address allocation. It's a large, important question that we're just up to. In these test beds, the way we did it, because these are aimed at, let's see, there's 2 steps in answering that. These are aimed at building scale things. We're in a room like this. This would, say, be one Internet Zero network. And then the intention is not that you can talk to the light bulb from China, even though you couldn't. In fact, it led to some funny debugging where we accidentally did do that. But from here, you go up through the hierarchy of the internet, and so there's levels of aggregation above it. So in this case, we just did randomized addressing. You could do more organized addressing schemes. So among the partners working in this are people like JP Vesor and Ralph Drams at Cisco of IETF gurus who've been looking at these questions of if you have huge numbers of IP devices, and in particular, if they don't have MACs, how you do addressing. So we're answering that question on this scale. It raises larger questions beyond us that we would invite collaboration on.
So can you talk about what will the energy source be for your linear self-folding string at the mesoscale?
Say it again. What?
What will the energy source? You want thermal energy is not going to work.
Oh,
for
this is how we're going to physically make this. Yeah. There isn't a single source in that we're doing versions of that where those blocks are centimeters, millimeters, and microns. And it's a different answer for each of them. And there's also versions that are rewritable and write-only. So the write-only is it's elastic energy, and it's done by weaving, essentially. The electrically driven version, you're sending power down the backbone, so you're not storing power locally. But the communication bus is also a power bus, passing power locally. And then in the microscale version, these are micron droplets, and so it's surface energy of droplet-droplet adhesion.
Where's the energy for the space exploration?
What is the energy for the space?
Where it's exploring the space. Right? So
You mean in this video? Again, in each of the ones I showed you, there was a different answer. So in the elastic answer, it's there's a mechanical elastic energy that's getting minimized in the local joint. In the electrical one, there's electropermanent magnets that are minimizing magnetic flux energy. In the droplet one, it's a droplet-droplet fusion. In each of those, there's a different physical energy, but the key attribute is those were 3 different interactions, but they're local interactions of local joints. And so each joint is minimizing the physics of that interaction locally, and then you get this global forcing. Yep.
With the folding, do you ever have trouble with writing that to the first multiple?
Sure. So the question is, do we have trouble with paths that don't fold? By construction, no, in that I haven't talked about how the whole CAD workflow works, but it's based on what makes this interesting is a constructive proof of finding non-self-intersecting passes that are guaranteed to fold. So the question is not non-self-intersecting. There's now a more interesting question is, in protein folding, there's primary and secondary and tertiary structure in alpha helices and beta sheets. And we're finding the need for something like that in that it's a bad idea to do this all in one go. You want to make sort of motifs and assemble them. And we're starting to look at how you sort of map geometrical structures into these motifs. One of the things, in thinking about next steps in each of these, because almost out of time, I wanted to advertise on the ALA, we're making chips in these roles, but what may be closest to home is we're working in particular with the national labs on massively parallel simulators of ALAs as a way to program really big computers. So one area of overlap might be just given a whole pile of computing, this is a different way to program it. On the Internet Zero stuff, this is now getting commercialized by Cisco and Schneider and all of them, and is going into test beds. And so if you want to do IP to anything, that would be a route for this. And then this stuff is going, the thin servers, thinner clients is just going into field trials. And so another possible connection is to play with prototypes of that in the early field trials. OK. OK, then I'm here for the couple hours this afternoon, and I'd be happy to discuss more. Thank you.